Welcome back to our chemistry flipped classroom, and we're continuing our conversation about equilibrium. So far we've learned what equilibrium is, and we've talked about an equilibrium constant, and we've talked about the fact that the ratio of products to reactants at equilibrium is a constant, and we can write that with the equilibrium expression. And so today we're going to talk about what happens when you disturb a system that's already at equilibrium. So we're going to learn how to use this principle we call LeChatelier's principle to predict the effect of changes to a system that's at equilibrium. So whether we change concentration, temperature, pressure. And so let's jump in and talk about LeChatelier. So LeChatelier's principle, developed by Henri LeChatelier, says that when a system at equilibrium is placed under stress, the system will undergo a change in such a way as to relieve that stress. So what we're talking about with stress is that we are adding something that changes the situation, that changes the equilibrium. So when we translate this into maybe a little bit easier to understand language, we would say that if we take something away from a system that's at equilibrium, the system is going to shift in such a way as to replace what you've taken away. And if you add something to a system that's at equilibrium, the system is going to shift to use up what you've added. So really this comes down to the fact that that equilibrium constant is going to try and stay the same. And we can understand this from the perspective of anything we do. Remember, equilibrium is when the rate of the forward reaction and the rate of the reverse reaction are the same. And so if we change the concentration of any of the reactants or the concentration of any of the products, that's going to affect the rate of the forward reaction if we've changed the reactants, or the reverse reaction if we've changed the products. And so when we change those rates, then we affect our equilibrium. So the equilibrium point is going to stay the same, but the system is going to shift to try to come back to that same original equilibrium point. So when we think about like our little teeter-totter, right, if we put more weight on this end, then it's going to have to shift so that it can come back to that equilibrium. So let's look at a couple of examples. So if we have a closed container, notice that it's closed. It can't be at equilibrium if it's not closed, and it's at equilibrium, and we raise the temperature. So this is a pretty common sense example here, right? If we have ice and we have water in the same container and we add energy in the form of heat, we raise the temperature, we know that some of our ice is going to melt and it's going to become water. And so the equilibrium of the system is going to shift to the right to use up that added energy. I always like to start with this example because this one feels like common sense to us. So if we have an endothermic reaction, a reaction where energy has to be added to make it happen, if we have an endothermic reaction and we add heat, that's going to shift the reaction to the right. If we have an endothermic reaction and we remove heat, that's going to shift the energy to the left, or shift the system to the left to produce more heat. So it's always shifting away from something that's added and towards something that's taken away. So in this case, we've added energy. It's going to shift to the right to use up that added energy. So let's look at another example, one where we're changing concentration. So if we have a closed container of dinitrogen tetroxide and nitrogen dioxide, and it's at equilibrium, and we add some nitrogen dioxide to the container. Now, if we think about our equilibrium constant, we have just increased the number in the numerator. In order for us to come back to a constant, we have to decrease the number in the numerator and increase the number in the denominator. And that means that our system is going to shift to the left to use up that added nitrogen dioxide. So we can look at this from a more conceptual perspective of whatever we add, we have to shift to use it up. We can look at it from a mathematical perspective, thinking about that equilibrium constant, whichever way makes more sense to you. So remember, whatever we add, the system is going to shift away from that side of the reaction in order to use up the added compound or added energy. Okay, so now again, we're going to be looking at changing concentration, but we're going to do it this time by removing something. So again, we have our closed container. It has water and water vapor. We're at equilibrium. If I apply a vacuum and remove some of the vapor from that system, the system is going to shift to the right to replace the vapor that was removed. So if we remove something, then the equilibrium is going to shift to the side where that substance is found. So far we've talked about changing concentration. We've talked about changing temperature. Let's also talk about changing pressure. So we're going to go back to our example of the dinitrogen tetroxide and the nitrogen dioxide. Pressure only affects equilibrium if you have gaseous substances. So if we have this system, the equilibrium, and we increase pressure. When we increase pressure in order to adjust to that stress, in order to minimize that stress, we want to have fewer molecules, because remember, pressure is caused by the collisions of the molecules with the walls of the container. So if we want to reduce pressure, we want to reduce molecules. So when we look at this equation, we can see that we have 2 molecules on the right, on the product side, and only 1 on the left. And so when we're talking about pressure, if we increase pressure, it's always going to shift to the side with fewer moles of gas. So in this case, it's going to shift to the left. Okay. So adding pressure shifts away from the side with more moles to the side with fewer moles. If we were to decrease pressure, increasing volume, for example, then that would cause our equilibrium to shift to the side with more moles of gas. Okay, so notice that in all of our examples to this point, we have been talking about a closed container. If we have an open container, we can't really ever talk about an equilibrium that has gases in it, because if our container is not closed, our gaseous products are effectively going to be removed from our solution. They're going to leave. And so that's going to cause our reaction to go to completion. So here where we have the hydronium ion reacting with the hydrogen carbonate ion or the bicarbonate ion, it's going to form water and carbon dioxide gas. If our container is not closed, that carbon dioxide gas is going to leave. So that's going to keep causing this reaction to shift to the right. And that's going to mean that this reaction is going to go to completion. Now, if this happened in a closed container, that wouldn't be the case. So the equilibrium of our system is going to continuously shift to the right because the gaseous carbon dioxide is escaping and therefore does not contribute to that equilibrium. And then our last thing that we're going to talk about when it comes to LeChatelier's principle is adding a common ion. And this can cause the formation of a precipitate. So if we think about an electrolyte dissolving in solution, an ionic compound dissolving in solution, if I add some other source of one of those ions, then that can, in order to use up, so if in this example, if I added hydrochloric acid. So I'm adding some other source of chloride ions. That's going to shift this equilibrium to the left to use up the added chloride ions. And that's going to cause sodium chloride to precipitate out of our reaction. So just a quick review. LeChatelier's principle says when we take something away from a system at equilibrium, it's going to shift to replace what we've taken away. The thing that we take away can be a gas. It can be the concentration of one of the products or reactants. It can be temperature or energy. And it's going to shift to replace what we've taken away. If I add something to a system at equilibrium, the system is going to shift in such a way as to use up what I've added. And again, I can add energy, I can add substances. And then pressure, the system is going to shift to reduce the number of molecules. If you increase pressure, it's going to shift to increase the number of molecules if you decrease pressure. All right, as always, I look forward to hearing your questions and seeing you in class.